Alright, ladies and gentlemen, today's class recording has started. So, today we're going to start with this simulation that is similar to the lab that you guys did in class. So, I'm going to take this pendulum here, and I'm going to pull it back this far here, right, and then I'm going to let it go. And it does this. Woo, yay. Okay, so, now, there's a lot of different things that you can do with this simulation. We're going to use it to analyze some energy concepts and specifically conservation of energy. So, to do that, I'm going to add a couple things here. Over here on the right-hand side, there is there's a bunch of check mark boxes and things like that. And I'm going to hit this over here. It says show energy of pendulum number 1, and it's going to go just like that. Okay. So let's see if I can actually modify this a little bit. Okay. Oh, I'm going to go here. I'm going to go here. All right, we'll go 35 degrees. That'll work. And I'm going to let it go. And we see this happening. Okay. So, it happens pretty quickly. So here I'm going to take us from real time to quarter time. Okay. All right. So, as far as the bar graphs go, right, we can see that there are 3 bar graphs moving right here. One's labeled KE, one's labeled PE, one's labeled total at this point in time, okay? And first, as we watch the changes in the 2 graphs, do they make sense based on the motion of the pendulum? Okay? Because, well, let's talk about the 2 individual, let's talk about KE and PE first, right? What do we see? Where is PE the highest? At its highest point, because potential energy depends on height, right? And then KE is the highest when? At the bottom, at its lowest point, right? And we've talked about when you guys were, or if you were here yesterday when we were working on the lab, we talked about the idea that, you know, when you pull the pendulum back, just like I did originally in this demonstration, you are adding energy to the system, right? If I hit the reset button, right, the pendulum is at its lowest point, or like when we discussed in class yesterday, like a 0 height, right? And it's not moving, so right now it doesn't have any energy. When I pull it backwards, I'm adding energy to the system, specifically potential energy, because I'm raising the height. And then when I let it go, that potential energy decreases, but in response, the kinetic energy increases because gravity makes it go faster, etc., 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 right? And it just keeps going and going and going, right? So, question number 1. Is energy conserved in this demonstration? Yes, all right? First, let's make sure we define conservation, yes? It's a concept that I'm sure you've been introduced to already in several classes, right? So when we say something is conserved, what does that mean? We can go with we keep all of it, right? If we quantitatively analyze something, how can we see if there's conservation? What would we see? Total energy is going to stay the same. The amount of energy is going to stay the same, right? Quantitative being numbers, measurement, right? Okay, so if we quantitatively analyze something, we should see the amount of energy being the same. And even though the form of this energy keeps changing, what do we see about the bar graph labeled total? Keeps the same value, right? The composition of that value, whether it's blue or whether it's green, keeps changing, but the total energy remains the same. All right? Good with that so far? Okay. Now, some of you noticed yesterday and kind of brought it up that this is not real life, right? What happens in real life to this pendulum? Well, air resistance and friction cause this pendulum to do what? Slow down and eventually stop. So all of the energy that I gave it initially ends up going away, or doesn't, right? So because this is a simulation and we can do things that we can't do in real life, right? Over on the right-hand side, I have the ability to control how much friction this pendulum feels, right? So right now, it's at none. And when we see no friction whatsoever, or if we can isolate no friction, if we can have a system that has no friction, we'll see here that the total energy is remaining the same, but the form is just changing between one and the other, right? Good there? All right, let's add friction, and let's see what we get. We'll go about halfway on friction. All right, so observations, right? What are we starting to see now? Thermal energy starts increasing, right? Heat energy starts increasing, okay? So, question, let's answer it literally. Is energy conserved in this demonstration? Yes, right? What are we seeing about the bar graph labeled total energy? Stays the same, right? It's not changing. But we said that was the case in the previous pendulum, and this is a much different situation, right? In real life, we don't see that pendulum just keep going back and forth, right? So, when we talk about energy, we have to be a little bit more specific. This unit, for the most part, deals with something that we call mechanical energy, right? Mechanical energy is basically the energy that we deal with on an everyday basis, okay? The energy associated with, like we talked about the other day, basketballs, people, trains, planes, those kind of things, right? And we talked about that it consists of three kinds: kinetic energy, gravitational potential, elastic potential. In this situation, is mechanical energy being conserved? No, right? In this situation, mechanical energy is decreasing. The amount of potential keeps becoming less each time. And if the amount of potential becomes less on each swing, what does that mean about the height of each swing? It's going to get shorter and shorter than the previous one, right? And eventually it's going to end up in a spot where we began with no energy, right? Will it actually have no energy? No, it just has what now? What kind of energy? Well, at the end when it stops, right? If you no, like eventually what's going to happen? Like we said, eventually what's going to happen to this pendulum? It's going to stop moving, and it's going to stop moving at the lowest point, right where it started. At the beginning of the simulation, we said that was no energy whatsoever. When it gets back to that point, will it have no energy? What's that graph going to look like at the very, very end? It's going to look all red. So it will have energy. It'll just have what kind of energy? Thermal energy, right? So that mechanical energy that we put into it at the very, very beginning all gets converted into thermal energy, okay? So when we're analyzing a situation, we have to look at two different things. One, is energy conserved? And the answer is always going to be yes, okay? If we look at the universe as a whole, energy total is always going to be conserved, whatever form it may come in. But mechanical energy is only going to be conserved under certain conditions, right? Mechanical energy was conserved as long as we neglected what in our simulation? We had to get rid of friction, right? Which means, what is the only force that was acting on the pendulum at that time? Gravity. Gravity's a different force than friction is, a different kind of force. We refer to gravity as a conservative force. It's conservative because it doesn't change the total amount of mechanical energy. It just converts one form into another. Gravity changes the energy, it just changes forms. It turns kinetic into potential, it turns potential into kinetic, but we keep the same amount of mechanical energy. Friction is a non-conservative force because it turns mechanical energy into other forms of energy. Generally speaking, that's going to be heat, okay, or thermal energy. Good there? You okay with that concept, at least for starters? Okay. All right. Let's mess around with just a little bit, okay? And I'm going to reset here, okay? And I'm going to go back to no friction so we can talk about things idealistically, okay? Let's see if I can pause this. Good. All right. All right. So here, okay. I take this back just like we started before, okay? Let's mess around with some of the other controls on the right-hand side, okay? One of the things that I can do is take my pendulum to a different location, okay? What if I click the moon button? What should I see happen? How's the simulation going to change? What's going to change about the simulation? It'll fall slower. What's one initial change that's going to happen even before I hit the play button? Well, what am I showing over on the graph on the right-hand side? Let's go literally. What is the graph showing you on the right-hand side? Potential energy, right? And we learned earlier in this week that potential energy depends on three things, right? MGH, okay? Has the mass of my pendulum changed? Nope. Has the height of the pendulum changed? But if I click that button that takes it from Earth to the moon, what is going to change? The acceleration of gravity. How does the acceleration of gravity on the moon compare to the acceleration of gravity here on Earth? Hopefully we know this. It's less, right? So what should happen to my blue line over there? Ooh, turned it all into thermal apparently, but okay, that really doesn't happen in real life. Okay, but we just moved locations, all right? But changing that, yeah, there it is. So yeah, all of that energy that we had, we had to use it to get there, right? But we see that the potential energy line went way down, right? Okay. If I go to Jupiter, right? How big is Jupiter compared to Earth? Much larger, right? Way bigger gravity, right? And so we go here, right? Okay. That amount goes way up, okay? Good with those things, how that depends there. And then, okay, if we reset, we'll go to Jupiter, right? Okay. But with no friction, right? Okay. There it goes. Same thing as before, okay? As far as, here, let's talk about some speed and see what happens here. Does that make sense? Is why this is happening now? If we go from Jupiter to the Earth, less gravity, right? It's going to go higher than what we originally lifted it because of the fact that, right, the gravity takes longer to slow it down. It goes higher in the air, et cetera, okay? All right, making sense so far? At this point, okay. So let's put some words to this here, okay? So, all right, conservation of energy. Energy takes many forms: mechanical, electrical, thermal, and nuclear. Anytime work is done, energy is transformed from one form to another, okay? And so we haven't talked about work yet. That's going to be the next thing that we talk about here, okay? But work is a transfer of energy. We introduced it a little bit the other day, right? So work is a transfer of energy. One process might transform some kinetic energy into electrical potential. Another might transform some spring potential into kinetic energy. Anytime we transfer that form of energy from one into another, we're going to maintain the same amount of energy, right? And that's basically what the last bullet point is saying. To say that energy is conserved means that energy can never be created or destroyed. It can only be transformed from one form into another. That's how you learn the concept of conservation way back, whenever you learn it in 7th grade or whatever it is. But when we talk about analyzing that conservation, right, that means that if we measure it, it's always going to be the same amount, regardless of when we measure it. The total has to stay the same, okay? So, when frictional forces act on a system, such as when a car's brakes are applied, kinetic energy is transformed into thermal energy. So in that case, we're still conserving energy, but we're not conserving mechanical energy, right? Situations where all forms of friction be ignored, no potential or kinetic energy is transformed into thermal energy. In this ideal case, the sum of the kinetic and potential energies is always the same. So in that case, we would see a conservation of not just energy general, but specifically mechanical energy, right? Mechanical energy being kinetic and potential, right? The sum of kinetic and potential energies of an object is referred to as mechanical energy. Thus, mechanical energy is potential and kinetic. This means that mechanical energy is conserved, but we have to make sure we deal with this. All forms of friction can be ignored. Okay with that concept? Okay with that? All right. So at this point, based on that discussion, the analysis questions of the lab should make a little bit more sense, okay? Based on what you calculated, what you're seeing with your numbers, et cetera, et cetera, et cetera. Now, in looking at some of your numbers yesterday, a lot of them are not going to, they're not right, so let's go with that. Just throw it out there on the table. Because when we did our demonstration, right, when we measured potential and then we measured kinetic, right, the kinetic can't be any bigger than the potential it started with, right? At best, it could be the same. But in reality, what's happening to some of that potential energy that we started with as it goes along? Is this pendulum right here a friction-free setup? No, right? So in reality, we should see that the kinetic energy that you measured at the end should be less than the potential energy that you started with. But a lot of that depends on how accurately are you measuring your height, because that height determines the potential energy, right? So if you didn't accurately measure the height that it started, you might not get the right amount of potential energy, and you might actually see an increase of potential into kinetic. That's not actually what happened, but go with, when you're answering questions, think about it in the standpoint of the demonstration that we just talked about, okay? Good there. All right, so why don't we do this? You have about 10, a little bit less because we're on homeroom today, so we only get out like a minute earlier after homeroom, so. But anyway, yeah, apparently there's some letter that, some acknowledgement that you received the parent-student handbook. We have homeroom today, so you have about, like I said, 14 minutes until class is over. You can do a couple of things. One, you're working on the lab if you would like. Two, I did post I guess we did talk about the quiz, right? Anybody? Sorry. Should have talked about that first on the recording. If you go to the Google Classroom site, I posted a quiz, kinetic and potential energy. It's literally like 4 questions. It might be 5 if I remember right, but it's about kinetic and potential energy, the relationships between speed and kinetic energy, height and potential energy, et cetera, et cetera. You can work on that now if you would like. A lot of my physical science kids, I do these quizzes more with my physical science kids, and a lot of them are doing them in class, and they're just like getting them done on their phone, and it works out pretty well. You can do that if you would like to, or you can continue working on the lab. That would be cool too. Tomorrow we'll look at some examples and do some sample problems dealing with conservation of mechanical energy and see how that works all out mathematically. Okay? Good there? Questions? Okay. Be productive for the last 15 minutes.